So first off, I have to say that this project, or this article that we're talking about, is part of the Linear Haskell project, which, despite the name, is not really about Haskell. It's much more about the linear part. It's Haskell only because, we have to choose a language where we do the thing. It's only because I, value my sanity. Usually I would, in my first slide, put the pictures of all the people that worked on the project, but there's quite a lot now, and I kind of gave up. So instead I put a little timeline and put today for scale. So what's Linear Haskell? The goal of Linear Haskell is, to add linear types, and we've made a lot of progress to Haskell, or to any programming language that already exists in a certain sense. So we're focusing on Haskell, though. So I'm not going to mention any other programming languages from now on. But I'm sure it works in any. So to explain for a second what a linear type is well, the idea is to add an extra function type. There's a number of ways to do that that are like more or less equivalent and have pros and cons. The way we've done that in Linear Haskell was to add just a new arrow, which we write a %1 arrow. And a function of type A, linear function B, I'm going to read that way, promises that it uses its argument only once. We really say if the result is consumed exactly once, then the argument is also consumed exactly once. And Arnaud, you would say, why do you need something like this? Why would anybody need something like this? Well, hypothetical audience member, this is an excellent question. The thing is, producing a linear function from A to B, doesn't buy you a lot. Okay, I made a promise, but it's not really useful to make that promise. What is useful is to require a linear function from A to B, because it lets you constrain how your API is consumed. You can, for instance, force some resources to be used in a single-threaded fashion. And once you've forced single threading, then you can do all sorts of things, like allocating data with malloc directly, bypassing the GC, and still be memory safe. I'm not going to do quite that today because it's a bit involved for slides. So we're going to do the simpler version, which is just to have mutable data structures. So I'm going to pop up some code for a mutable array. So what's interesting about that is not only do I have a mutable array, but I have a pure interface. So really what I'm saying is I have a data structure that is a pure array, but under the hood, I'm going to implement that by mutation, because presumably that is much more efficient. Possibly, it really depends on what you're doing. You give up sharing, though, so it's not free. But that's not the point I'm getting at. The point I'm getting at is the code on the right is really ugly. And if you look at the code on the left, that's written in the Mezzo language, another like SIG plan-friendly language. It's exactly what I would have written naturally. Here we write swap, we just exchange two values, to positions in an array. All the examples in this talk are absolutely extremely contrived because, slides. Yeah, I'm a bit jealous. And, on the one hand, it's understandable, right? Mezzo is a language that's best spoke to speak about mutation of data structures, including arrays, etc. It's made for that. It has a dedicated type system. And I have this general purpose mechanism, a single type that I've added, a single type constructor that I've added to the language on which I'm encoding the thing. So you would expect some degree of boilerplate. It's never free. On the other hand, I'm jealous. But I mean, more seriously, I don't know if you've noticed, by the way, the syntax highlighter decided, like I named my arrays of A's and decided to pass that as the keyword as, which doesn't exist in Haskell. But it has like two interesting properties for today. First, it's very funny. And second, it highlights how ugly the code to the right is and how many times I wrote A's. Granted, I made the effort to make it look as silly as possible with all these prime signs. But the general idea is here. I've named the same array 4 times. And I mean, we're accustomed as pure functional programmers to return a new data structure when we modify it. But in that case, we even need to return a data structure when we read it, which... And so, considering this, I think this is just not very nice. It's like half the code here is just renaming the array, or quite half the code, but in a significant proportion. It obscures the idea. It makes the experience not very pleasant. I think that people tell me that. And so my users, that's you, by the way, I'm not going to use that. And honestly, I mean, just figuring out that something is single-threaded is something that any computer can do, right? It doesn't really need me to tell me, yeah, that's because that's A prime and not A, and whatever. So I wanted better. There was, by the way, there was 4 other authors on this paper. I don't mean to represent their motivations. Everyone has their own, but that was mine. It runs a bit deeper than this, but for today, we'll just focus on that. And if you want to know more, well, you come to see me tomorrow. So the trick, or the important point, and Frank did a lot of my job for me, thank you, is how does GAC, in that case, handles implicit things? Like, how do I make GC do work for me? So I'm going to clean up this. So these things are called constraints. They appear both in the type inference algorithm and also in terms, which is going to be our point. Just clean it up so that we can see. So when I'm doing inference, much like in the previous talk, so when I is GHC in that sentence. I don't know why I'm identifying all of a sudden. So GC walks down the term, says, okay, so I see an application, I want this to be equal to that, or I see an EQ constraint like at the top, and I say, oh, by the way, if you call nub, you'd better be able to satisfy the EQ constraint. And generates all that, and in a second phase would solve the constraint with a constraint solver. And on the other hand, like every constraint, more or less, can be manifested to the left of a fat arrow like this. So I can, as a programmer, even if I don't 100% need to, it can be helpful for my API, I can just put a constraint there. And I'm saying, when you use this API, you need to do this, but mostly GAC will do that or yell. And that's exactly what we want. We want GAC to tell me, this was single-threaded, I dealt with it, or yell. And so the core idea that we have here is to take this... Oh, sorry. I'm getting ahead of myself a little, sorry. So another important point that we will need is how is this fat arrow implemented? This fat arrow is desugared, ultimately, to a thin arrow, a perfectly normal arrow. So in the intermediate language of GAC, called core, the IC thing becomes an argument. And so that's where the ID comes from. Let's add a new fat arrow with a person 1 in front. We'll call that a linear fat arrow. And its meaning is given by the fact that desugars to a thin linear arrow. So if I do that, we need to pull that off, but give me a minute. Then I can write code with some linear constraints things in it. Let GAC infer what I need, and the meaning of this is just given by the linear array. So you don't really need to add any real power to JC, except to tell JC, oh, you can infer that. Yeah? Yeah, so the type of set doesn't fit the slide. I tried to make it smaller, but then it became very small. That being said, the slide is so big, I probably could have pulled it off. I realized that this morning. With that, like I wrote set, and of course you need a new get, etc. There's things to, you can write code for swap, it's the same function, and now it's, I mean, there's boilerplate. But there's not like silly boilerplate. Something you notice is that there's a single as on the slide, right? It's all in red, it's really convenient. There's a single as on the slide. This is not the linear quantity anymore. The function doesn't say, oh, I'm going to use a single M array, so it has to return a new M array to pretend it, you know. Instead, the only linear quantity that we have is this read-write constraint, which says I can read and write on my array. And because it's completely implicit, I don't get to see it. I just get an error message if I do something silly. And so that's what we set to do at first. But as it happens, there was another thing in Linear Haskell that was displeasing users. And if I'm allowed to go back to what I said very, very early on, I said that producing a linear function is not very useful, doesn't buy you much. What you need is require a linear function. So if I am to write a mutable array library, a pure mutable array library, I will have to ask for a linear function at some point. And the way it typically happens is when you create a new array. Create a new array, you don't return the array because it would be unconstrained. I don't really have time to go over this. You have to take a function that takes an array as an argument, consumes it linearly, and returns something that is not linear. That's what the thing means. Yeah, do you like that? But most people don't. I mean, it's not as bad as it looks in a way, because you will have to kind of scope any resource to say the resource exists in this scope. That's why I call that a scope function. It exists in the scope, and why not have the scope be delimited by a function? But the thing is, it does really cause problem. Like this, despite like this, I mean, I gave an example here. It's very tiny, so it's ugly, but whatever. But it does cause problem down the line, especially when you want to create several arrays and you want them to interact. It's quite messy, and it didn't work. And well, I forgot to. There's an issue on the linear-based library that I wanted to link there. I'll add it after the call, after the talk. The slides are online, by the way, but I haven't given you the address yet, so you don't go to your computer quite now. So it caused a lot of problem, and mostly it's unpleasant. It's not the way people want to look at new array. And a lot of people, so that's a probably more important problem. A lot of people so far that have designed linear API has gotten this wrong at least once. So they written a new array type function in direct style, and the API was not safe. So at the very least, it's not intuitive. And so enter the linearly constraint. There's a bit of a magical constraint. It's harder to implement the linearly constraint than just linear constraints in general. And it's a special constraint that has some properties because it needs to support contraction and weakening. To be completely useful. But then you just say, okay, I'm creating a new array linearly. And you just say that. Now the type fits the slide. And I think it fit before, yeah, but it was a bit too big. Now it's quite convenient. It looks okay. And then I wrote the fromness function in direct style, which is I mean, what we want to write for from list, but also this is not the right type for from list. So I said all the examples were really contrived. That's the best example so far. The best example of examples being contrived, I mean. And yeah, so how do you pull that off? Because so far that was wishful thinking. It turns out it's not that hard. So you can design a declarative system with constraints. The system is close enough to like vanilla linear Haskell without constraints so that the sugaring becomes obvious. You elaborate that with a constraint generation algorithm. There's a few things to think about because of linearity. You solve the constraint. Some people have already done that, making constraint solver for this language. They just didn't know. But I'm very glad that they did the work for me. And for the rest, you'll have to read the paper. There's 15 pages of the technical development, so it goes into more details. Until then, you can follow the Tweag's blog, where I blog about these subjects from time to time. And here are the slides. The QR code also brings you there.